Okay, as you can see right now, in this video we'll be talking about problems 13 and 14. So let's look at problem 13 first. Determine how many integers n that fulfill all the following conditions. So 1 should be lesser or equal to n, and then n should be lesser or equal to 1000, and then the digit sum of n is odd, and then the digit sum of n plus 1 is odd. So okay, now let's observe some few things. So maybe let's say a random integer, right? So maybe I say 657, and then if I plus 1, then it will be 658. And then here we will have a digit sum of 18 and then a digit sum of 19. So this means that it's consecutive. So, and then we do another one, maybe say 253 and then plus 1 would be 254. This one has a digit sum of 10, and then this one would plus 1 would be this one will be having a digit sum of 11. That's also consecutive. So since we might have the fake impression that all the numbers, when maybe two consecutive numbers have two consecutive numbers have consecutive digit sums, is that true? Well, it might be true, it's partially true, but it's not all of them. So if we say our units digit, so this is units digit, if our units digit is ranging from 0 to 8, and then plus 1, we will have 1 to 9, right? So of course this one would be, how should I say, this one would have consecutive digit sums because you are not changing the tens digit or maybe the hundreds digit. But magic happens when your, your units digit is 9. So take for example, maybe say 139. So this one has a digit sum of 13. And then if you plus 1, this one will yield 114, and then this one has a digit sum of 5. So one of the solutions for n is 139, to be honest. Yes. And how many of there? So now the first observation we make that for all n's that fit these criteria, so n must have a units digit of 9. Okay, so maybe something like that. But then what about if I say I put two 9s together? So wait. Okay, before I talk about this, let me talk about this one first. So provided that if tens digit is not 9, so maybe say 289, this one will have a digit sum of 19, and then plus 1, 290. This one will have the digit sum of 11. So so like this, I don't know how I need to explain. I'm very anxious right now. So 571. So an example will be 579 plus 1. So the workings behind this would be your units digit would have a deficit of 9, should I say so, and then your hundreds digit will not change because provided that your tens digit is not 9, and then your tens digit will actually add by 1. So here we have 580. So the net change in the digit sum will be -8. So actually this one preserves a thing which we call parity. Parity I can't explain much here, but it's just odd and even. So if I say 579, the digit sum is odd, then 580 the digit sum will still be odd. But if I have 299 for example over here, and then I add a 1, so what we have is the hundreds digit will have a gain of 1, and then our units digit, our tens digit will -9, and our units digit also -9. So this one will be 17. And this one needs to fit the condition that this hundreds digit is somewhere between 0 to 8, because you can't 999. If it's 999, then plus 1 you will get 1000. So 999 has a digit sum of 27, and then 1000 has a digit sum of 1. So this one is an exception, but this one will consider it the one case. Okay, now let me erase some things first so that we can continue better. Sorry for me stuttering so much. And now we need to write our second, preceding conclusions. So say K99. So K99 with a line on top of it, it actually just means maybe if k is 1, then it's 199, because if we just write like this k99 without a line on top, maybe some might assume to be k times 99, so which is not true. So this k99 with line on top cannot fulfill criteria except for 999. So 999 is one case. And then for third, okay, now that we know that n must have a units digit of 9, and then k99 cannot be accepted except for 999. So now we know our units digit is 9, and then now we need to simply fix our hundreds and tens digit. So maybe say our hundreds digit is an even number. So if hundreds digit is even, so for example say 2 or 0, 0, 2, 4, 6, 8 all count, okay? So if this is 2, so this one is already odd. So what we need to add over here is another even number. So in this case, maybe we can say 6, okay? So either even or odd and odd. So the hundreds digit and tens digit must add up to be an even number, and then we have a 9 at the units digit. So maybe say this one, for example, 1 and 3, okay? So if even, we can have our hundreds digit as 0, 2, 4, 6, 8, and then for odd we would have 1, 3, 5, 7, 9. And then note that for the tens digit we also can have 1, 3, 5, and 7, but 9 cannot be accepted except for 999. So this one is a very confusing place. So 9 cannot be accepted. So now we have in total, so we have 5 times 4, we'll have 20 cases. You can pair it up by yourselves, and then plus a 1, which is the exception, which is 999 over here. We will have 21 cases over here. And then for even cases, if I'm saying that the hundreds digit is 0, it just means maybe say the tens digit is 69, then our number will just be 69. There won't be any 069, just to clarify. So here we have 5 choices for even hundreds digit, and then for our even tens digit we'll also have 0, 2, 4, 6, 8. So 5 times 5 is 25. 25 plus 21. So 25 plus 21. The number of cases for the number of n which fit the criteria for problem 13 would be 46. So I'm sorry that I have been stuttering for so long. Now let's look at problem 14. So as I erase, I'll be explaining a little bit about problem 14. So problem 14 states that which 4-digit perfect square starts with 2 equal digits and ends with 2 equal digits. So the number must be in the form of AABB. Okay, so we are a very quick one. So the number must be in the form of AABB. Recall that when I put a line on top, if I don't put a line on top, it will just mean A times B times B, so which is not. We want to express this in decimal form, so we need to put a line on top. So this one is actually, how do I say, 11 times A times 100, because how do I say, this one is AABB is AA00 plus BB. So this one is actually A times 100 times 11, and then we have B times 11. Okay, noted. So note that A and B should be, A should be 1 to 9, and then B should be 0 to 9. Okay, so it's a single digit. So we have this perfect square is 11 times A0B. Okay, so since we have a perfect square here, so what this means that because we have a 11 out here, so singled out, so this implies that within this AOB is another multiple 11. So recall that when I use this line, it means that 11 is a factor of A0B, or A0B is a multiple 11. So regarding divisibility by 11, what we will do is we will add the alternating digits. So this one will be one group, so this one, in this case, this one will be A plus B, and then for even digits, we will put it in another group. In this case is 0, and then we will subtract the 2. So A plus B minus 0 is just A plus B. So this further boils down to 11 is a factor of a plus b. But recall that a and b only have a maximum value of 9, and then 9 plus 9 is 18. And then the only multiple of 11 below 18 is 11, because a and b cannot both be 0. So we know that a plus b is 11. And then maybe we can have, so a and b are single digits, so maybe a, b could have a value of 2, 9, and then can have a 3, 8, and then so on and so forth, and then to 7, 4, and then to 8, 3, and then to 9, 2. So if we yield it out, this one would have, if we do so, our AOB would have maybe 209, 308, and then so on and so forth. And then now I want you to recall something, which is for the units digit of perfect square numbers. So I'll use an abbreviation. So perfect square numbers, they will only have choices like 0, 1, 4, 5, 6, and 9. Okay, so our b can only have our b cannot have 0 and 1. So these two are already not inside the list, and then only 4, 5, 6, and 9 fit the criteria. So this one delete. Okay, so now we boil down to, we only have the possible values of a, b are what we have. Let me write out. Sorry, I'm taking so much time. Okay, so units digit of PSN 4, 5, 6, 9. So we have this one. If this is 6, then this one will be 5, and then this one will be 6, 5, and then the last value will be 7, 4. Okay, so our AOB would be either 209, 506, 605, or 704. Okay, and then now another characteristic of perfect square numbers is maybe say some number b squared. These two are not the same. I'm just using an alphabet to explain what I want to intend. I don't know. Okay, so b squared will have, in mod 4, modular 4, when divided by 4, it will either have a remainder of 0 or 1. Okay, so I'll repeat. A perfect square number, when divided by 4, will have a remainder of either 0 or 1. So now let's check AABB. So now our AABB, maybe I'll have to erase these first. Okay, so our AABB has 4 different values, so let me write them out. Our AABB has values of maybe 2299, 5566, 6655, and then 7744. So 2299 when divided by 4 will have a remainder of 3, so I'll be using mod 4 over here. And this one I'll also erase to make some space for my video. Okay, so 2299 when divided by 4 will have a remainder of 3, so this one is eliminated. And then this one 5566 when divided by 4 will have a remainder of 2. 6655 when divided by 4 will have a remainder of 3, and then 7744 will have a remainder of 0. So these three are actually not suitable, and then our final answer will be 7744. If you check the answer, so 7744, if you put a square root above it, it will yield 88. So yeah, 88 squared is 7744. So our answer to problem 14 would be 7744. Okay, and yeah, so this is the end of the video. I think the following videos will also take a much longer time, considering the fact that this is the senior paper we're talking about, and then doing the paper and explaining the paper, the questions in the paper are two entirely different things. So yeah, I hope you guys have taken something out, and then I'm so sorry if I talk too fast. We'll see you guys in the next video.